Hello, Calc. It's February 17th, and you can watch this after Friday's class. As I promised, I'll be up late on Friday night. And then there's Saturday, Sunday, or Monday. Sometime before Tuesday's class, please watch this edition of Area Under the Curve. We've started approximating the area under the curve with these rectangular boxes, sections under the curve, and these are called Riemann sums. Anytime I take a curve and divide the area under it into subintervals and make rectangles out of those subintervals, I am creating Riemann sums. I'm going to add them all up and find an approximation of the area under the curve. So we're always breaking these into sections, and the sections become some forms of rectangles. But there's lots of flavors. There's upper Riemann sums, lower Riemann sums, there's left sums, right sums, and then there's another form altogether called the trapezoidal rule. And that's another one. It's not a Riemann sum, but it's another way to approximate the area under the curve. So I'm going to talk about these 5 ways in theory, and then I'll do one. I'll take a problem and we'll do an upper, lower, left, right, and a trapezoidal sum on the same problem, so you can see how it looks. All right, let's go ahead and think of, say we have a curve, and some of this is repeat. Alright, so you've had a couple days with these boxes. So say there's a curve like this. It could be between 0 and 2. And I'm looking at 4 subintervals in between. So I'd be able to calculate, if they were of equal width, I'd be able to calculate the width of each to be 1/2 from here to here, here to here, here to here, and here to here. So the width of one of these subintervals is 1/2. And that's true for each one. And if I'm going to start with, say, which one should I start with? How about left? Left Riemann sums. Left Riemann sums, we'll go into each one and we'll look at the left side of the section. So here, going from right to left, this section, we're going to look at the left side right here. And where that connects to the graph, we're going to create a box. So here's left, left. This left is at 0, so it kind of degenerates into no box at all. So those would be the left Riemann sums, and we could calculate the height of each one by noticing that it is on the curve. And you would know the name of the curve, so it's in theory here just f of x. So we would go 1/2 for the first box. Now I'm going from left to right. The first box is 1/2 wide and 0 high. And the second box is 1/2 wide, and it is what this value is at 1/2. So it's f of 1/2. We'd have to put 1/2 into the function and find out how high that box is. Then we would put 1 into the function times 1/2, and then we'd put in 1.5 into the function and find out its height. Then we would add that up and we'd have our left Riemann sum. Alright, if we were doing a right box, we would take the same sort of function, divide it into 4 subintervals, and we go to the right side and we create a box. Right side, create a box, right side, and this time we have 4 heights. And we would take this time, this is supposed to be on the function, so I'll make it big. And this is on the function, the height of this is on the function, the height of this is on the function. So going up from left to right, we'd have 1/2 times the function evaluate. If this is 2, this is 1, 1/2, 1 1/2. The function, the height of this box is f of 1/2 plus 1/2, going to this one, f of 1 plus 1/2, f of 1 1/2, and plus, well, that's the last one. No, it's not. So we're doing the right Riemann sums. So the right side was this one, the right of this was this, the right of this, so we did have one more. The right side of this last one is 1/2 is the width, and the height is the function evaluated at 2. Alright. Again, this is theoretical because I didn't give you the name of the function. You can't evaluate it. So then we could let's look back at these and talk about lower boxes. It turns out that when you do 4 subintervals, you look at the section that was sectioned off. Let me write that. Let me start from scratch. 4 subintervals. And lower boxes means you say you look at this section. You're going to take look at the top of your section, your soon-to-be rectangle, and you find the lowest spot along the top of this section. It's right there. And you create a box. Here, the lowest, here, the lowest, and here, the degenerated box. Notice the lower boxes are the lower Riemann sums is the formal name. Looks identical and acts and works identical to the left Riemann sums in this case. But let me show you one where it wouldn't. Suppose our function didn't continually rise. Suppose it went like that. So that function would have 4 sections, and you would create the boxes by going to each section. Say this section first. Here's the lowest point on this section, creates a degenerated box. Here the lower one would be here, the lower point. On this subinterval, the lowest point would be there. And this one, again, is no box at all. So we would just have this to calculate. So lower boxes don't always work like these left boxes did, but in some cases they are identical. So that's what a lower box would do. An upper box, you would have the function, and you would go 4 subintervals. You'd go along the top of the subintervals, and this time you'd go to the upper. So this is an upper Riemann sum. And you find the upper spot and you make your box. This section, the upper spot, and make your box. And let me make sure that's showing up. Good for you. This section, we want the upper spot and the upper spot. Again, that one turned out like a right Riemann sum in this case, but it won't always. All right. So that you understand how those are formed, let's look at a trapezoidal box. So we did right, left, upper, lower. Okay. trapezoids, you'll recall, look like this. Two sides are parallel and two sides are not parallel. This would also be a trapezoid. So we have two sides parallel, two sides not parallel. So our sections are going to look more like these trapezoids than these. So the area of a trapezoid is going to be 1/2 times the height of the trapezoid times the base 1, the length of base 1, plus the length of base 2. Alright, so keeping that area formula in mind for a trapezoid, let's create that sort of thing. So we have a section like this, divide into your subintervals, and this time I'm going to start over here. I'm going to take this spot and this spot, so the sides of the subinterval where they attach to the function, and I'm going to create a trapezoid by drawing a perfectly straight line from point to point. Alright, and here, perfectly straight line from point to point. Here, straight line, and here, straight line. Alright, these create 4 trapezoids. This degenerated to a triangle, but we can still use the trapezoidal rule. It's just that one of our bases is going to be 0 right here. So do you see the trapezoid? So here's the 2 parallel lines that correspond to this, but the height is going this way, so that takes some getting used to, but that's the height, and this is base 1 and base 2. It doesn't matter which you call which base. So just for this trapezoid, I would get the area of 1/2, which is in the formula. Ours, if we hold to from 0 to 2 for subintervals, we would have 1/2 again. For the height of our trapezoid, which corresponds to the width of the subinterval, and then this base would be the function evaluated at 2, plus this base would be the function evaluated at 1 3/4. Oh, 1.5, sorry. Which reminds me. Alright, 1.5. So that would take care of that one. And we would go down the line in like manner. So we would add for this one 1/2 times 1/2, the width. Then the function evaluated, if this was 1.5, this would be one of the bases of this trapezoid. It was also a base of this one. So we use it again. 1.5, the function evaluated 1.5 plus the function evaluated at 1, and so on. Down to this one, the function evaluated at 1 plus the function evaluated at 1/2. And even though it's not a trapezoid, the rule will work. We'll have 1/2 times 1/2, the function evaluated at 1/2 plus the function evaluated at 0. Alright, then we would add all that up. I forgot there's another Riemann sum, which I should have introduced, and that was the midpoint Riemann sums. So this trapezoidal rule is not really even a trapezoid. It is a trapezoid. It's not even a Riemann sum, but it is a way to approximate the area under a curve. So we're learning about it in this section. Alright, we'll go back and grab our Riemann sum called midpoint. So I'll shut down and start on part 2.